Good evening, Bulldogs. This chapter, chapter 4, is called Foundations for Inference. I've been trying to find a visual to give you guys so that you have a cue as we go, so that you don't get lost in the minutia of this chapter. It's going to be a lot of equations and several different ideas thrown around, and it can be overwhelming. But it shouldn't be, because at the end of the day, what we're trying to do is estimate a population parameter. So something where something is of interest at the population, and we need to find out what that something is. And we have tools that help us understand how good our estimate is and how much confidence we should have in our estimate of these measurements. So, for example, I like the way the text has it. In the language of statistics, the average weight of all U.S. adults is a population parameter. The mean weight in a sample or a survey is an estimate of population average weight. The principles of statistical inference provide not only estimates of population parameters, but also measures of uncertainty that account for the fact that different random samples will produce different estimates because of the variability of random sampling. Or more to the point of this image, if we were in this forest measuring the diameter of these trees, you can see that there's substantial variation in the diameter of these trees. And you might correctly assess that it would matter which trees you chose to sample, because if this is a very large forest, obviously you're not going to want to sample all of the trees. So the method of choosing which trees to measure matters, but even with that, there's an amount of uncertainty involved with the variability of the estimate with respect to the statistic, in this case the diameter that we need to measure. Actually, let's make it not a hypothetical forest. Let's make it a forest that you happen to be on vacation, and you realize that a place you've been going to for a number of years is probably going to burn. And there's going to be a lot of fuel for this fire. Now, not all of us are foresters. I'm not. So, kind of have to do what we can and document what is in this forest. So we measured 2 of the trees that were cut down. What do we think about this sample? What if we measured a bunch of trees? You'd need to know a little bit about the population that we're interested in to know whether or not this was an okay sample. Well, I'll go ahead and skip to the end and we'll come back. It wasn't a good sample, because what you see here in the red is the burned area as of today, October 5th, of the Mullen fire that is less than 9 miles away from where I took that sample. Now, I think we can all kind of understand why this would not be a representative of the trees that are in the burned area. Because I think we understand that trees can vary. If we were trying to measure the diameter, then maybe we would want to know what the mean diameter is. There is a true mean diameter of the trees in this forest. That would take forever to measure. So what we ought to do is take samples from different places that are representative of the forest of interest. All the while, though, we know that there's some uncertainty about what that true population parameter, the true population mean. And while we're at it, we probably need to make some estimates about the variation between the trees. What are the measures of dispersion for the tree diameters? There exists a true parameter for that as well, but we're going to have to settle for sample statistics. So let's get to it. We'll have a little more introduction to these ideas, and we'll talk about populations versus samples, confidence intervals, hypothesis testing, and merging tests, and confidence intervals. Inference uses the concepts of probability and the tools of data analysis to draw inferences or draw conclusions about populations by way of samples taken from the population and to estimate the uncertainty associated with this estimate. So, populations versus samples. Just to remind y'all from the first chapter, population is the larger group of interest. So all Americans, all college students, all of something. The sample is a subset that we choose to ask questions or measure in some way so that we can understand the larger population. So the text has this example of the Youth Risk Factor Behavior Surveillance System. The population in this would be U.S. high school aged youth. There are clearly more than 2.6 million high school aged youth over the period of 1991 to 2013. The dataset has 13,583 rows. Each of those rows represent a single person who took the survey. Here we have a display of some of the variables and some of the cases. And this is all from the R software that is often used for statistical analysis. The data starts down at the lines where there's a double hashtag or double pound sign. And you'll see that there's a 1, 2, 3, and then the 13,582, 13,583. Those are like an identifier for each of the individuals. So imagine you took the survey, one of these would describe you. And maybe if you were 14 when you took it, and you're a female, and you were in grade 9, and you didn't give him height and weight for some reason, and you never wear a helmet, and active 4 days a week. So then, just for example, if that were you, but it's somebody. That line represents somebody. The columns all represent something about that somebody. So again, you have an identifier, you have their age, you have the gender, grade, height, weight, and it turns out that there's actually a lot of these types of columns. We just only see a subset of them here so that it fits nicely on a slide. The same for respondents, or the individuals taking the survey. We only see 5 of them, We see the first three and presumably the last two. And that's just so that it fits on a page. It's a good idea whenever you have a data set to write this down. So having a little bit of a description for each variable is a good practice. The CDC used responses of these 13,572 students to estimate health behaviors of a target population. The target population is the 21.2 million high school age students in the US in 2013. We use the symbol mu, that's that U looking thing, it's mu, is used to denote a population mean. For a variable, such as weight, you might subscript it, so you have mu weight. We would really like to know the mean weight of these high school students, these 21.2 million high school students. And that's what mu represents. There is a mean weight for those students, but we don't know what it is. Asking 21.2 million students that question seems a little overwhelming. So we need to take samples, and that's exactly what you're looking at, is a sample of those students in this data. The symbol x bar, or x over bar, is used to denote a sample mean, and again you can subscript it with the weight. This is our estimate of population, but it's a sample mean. Now suppose that we were doing a study and then another class drew another sample and another 13,000 students and sampled them. Would our x bar, our mean weight for the sample, be the same? I would be extremely suspicious if it was the same. The point estimates will likely vary somewhat. I would expect a sample size that large to be relatively close or to the population, but not exactly equal to. Let's pretend, just for the sake of example, that our sample that we have is actually the population. So we'll let mean weight in this dataset be the population parameter, mu weight. And we're going to take a sample, well, maybe 10, to calculate x bar weight among the sampled individuals. So let's take a sample size of 10. And yes, this is our code. Don't get wrapped up around the code. I'm going to talk you through it because I think it's worth telling the story. But again, don't get wrapped up around the code. The code is just the language, and I'm going to verbally tell you the story. The first thing to notice is that the hashtag symbol, the £, where like on the top line it says load the dataset, that doesn't really do anything. That's just telling you what's happening in words. Then it says library, and it says something, and data, and then YRBSS in quotes. That's just loading the data. So the data set that we've been talking about, that's just putting it into the computer memory. Then we tell the computer how big the sample size is. Sample size could be, the word sample size could be anything, but in this case, just to keep things simple, it says sample size. Here in the next section, we're going to obtain the sample of row numbers, a random sample of row numbers. We have to set a seed if we want to be able to draw the same numbers again later, because computers, when they generate random numbers, it's actually a quasi-random process, but I don't want to go down that rabbit hole with this video. And just we have to set a seed to make sure that we have a way of reliably drawing the same number if we were to repeat this experiment in 2 weeks or something. The next section here calculates the mean of the weight for the sample rows. So these are the rows of individuals that we're choosing to sample from the population. Finally, we calculate the standard deviation of the weight of the students we sampled. No, that didn't hurt too bad, did it? If you do this repeatedly with, say, samples of 10, 100, 25, and 50, you can then plot histograms. In this case, I've converted it such that it's density rather than the count of, so it's the proportion of observations, or actually means, that are at a certain weight. And I've overlaid a density plot so that it just smooths out and shows the density and what the distribution of these means is as you change sample sizes. Now, you'll notice that as you move towards the larger sample, so the yellow one's the tallest and thinnest, and the 50 is the next in line, you get closer and closer to what we believe the population mean to be. Turns out that the population mean here is 67.9065. And I'd say it got pretty close.